Okay, so a lot of different ways that we can approach this problem. The convenient, so the most convenient one is to say that, well, this looks like something that I don't exactly remember off the top of my head what it looks like, but this looks like something I could attack with rotational symmetry. I just can't actually attack it with rotational symmetry because the 4 and the 9 are messing things up. Well, in particular the 9. Right. So what I am going to say, though, is that this is a stretched out version of something that I can understand more easily with symmetry. So let's start with, forget that guy, let's start with this similar equation, which is x squared minus y squared plus z squared equals 1. And so we'll get to the stretching later, but if I understand this, then I can just, you can see how I can use a stretching process to invert, to conclude what that is. Okay. All right, so let's understand this guy. Well, this has a rotational symmetry because I see right here that x and z appear only in that special form. So this is rotationally symmetric around the y-axis, right? And in fact, is this one that I did in the book already here? Yeah, look at this. I already did this one. So let's take advantage of that. I'm sure I did that on purpose. So figure 221 right here. And there is a picture of our sort of rotated surface. So here's the explanation if you want to see those details, but I'm going to skip that part at this point. Okay. All right. So this surface looks like that. Cool? Yeah. Okay. Now, that's not what I'm interested in, though. I am actually interested in this surface. And again, it's a stretched out version. So I have to ask myself, algebraically, what happens? What would I have to do? What sort of substitutions would I have to make in order to convert that equation into this equation? Well, I'd have to do two things. I'd have to, everywhere I see a y, I'd have to replace that with 2y. Right? And then everywhere I see a z, I would have to replace that with 3z. 2 and 3 instead of 4 and 9 because of the square. Okay. All right. So now I just have to ask myself, well, when I do these algebraic sort of substitutions, what is the corresponding geometric effect? And the corresponding geometric effect is that it is squished by a factor of 2 in the y direction, and it's squished by a factor of 3 in the z direction. So I'm going to squish it by 2 in the y direction, and I'm going to squish it by 3 in the z direction. And now the picture that I'm going to end up with is not going to be awesome, but it'll be, an attempt to recognize this. In fact, let's see if I can squeeze this onto the same thing here. I am going to get that out of my way first. Actually, maybe I should leave that there. All right, leave that. Oops. Yeah, we'll leave that there. Okay, so gosh, this is going to be hard to draw. Maybe I won't try to squeeze this onto the same figure. I will go ahead and give myself a new. And I'm just going to draw these circles twice as close to each other. That takes care of this. Oh, whoops! I didn't do a very good job there. Yeah. That's the fact. Squeezing by 2 in the y direction. But then I've also got to squeeze by 3 in the z direction. So that means I've got to make these shorter. Like that. And
like all Indian.
Yeah, they're ovals. That's right. And if you want to emphasize that these are ovals, you might actually put in here that it's that distance and that distance are going to be different. These are if that's K, then that's 3K. Just some indication. I mean, I could also try to refine my picture and make it look more like an oval, but in the absence of artistic skill, some indication like this is, yeah. Is that cool?
Mm-hmm.
Okay. All right, let me stop the recording here.